This tutorial is for intermediate motion simulation in NX. In this tutorial, I'm going to do a little bit more complicated mechanism simulation than I did in the beginning tutorial for Motion Sim. The system I'm going to use is a basic generalization of a piston cylinder engine, just a single cylinder engine with very simple parts. So I'm going to actually open these up now. I'll provide a link on the video in YouTube for where these files are if you're outside of the class. If you're in the class, then they're just on the IDE20.com website under the NX tutorials for tutorial 4. So I've got these already saved. So I have these all in a folder. I'm going to create a new part file as the assembly and then add these components into it. So I want to go ahead and do that now. So I'm just going to create a new assembly, and I want to make sure I put it in that same folder as the parts. Okay, that's the folder, and I've already got something called engine, so I'm going to call it engine 2. Inches. These parts were actually all drawn in millimeters, so I'm going to set it to millimeters, and I'm going to, sorry, I should have done that first. So millimeters assembly, and then I need to rename that back to engine 2. Okay, same folder. Alright, that looks good. Okay, so I need to go ahead and add these parts. Since they're not open in NX, I'll have to actually open them from here, and I should be able to select all of them. So I want the base, the crankshaft, the piston, the rod, and the sleeve. And you can see it puts them in a big giant stack down here. So I'm just going to put them in there and use absolute origin and then move them around as needed instead of doing it kind of step by step here. So I'll just put that in there, and then I've got a big mess of parts here that I've got to get sorted out. So what I'm going to do is go to Home. I'm going to, sorry, I actually need to move components, and I'm going to start translating these things and getting them lined up how I want them. So I want that there. And then I want this sleeve. I'm going to go ahead and rotate it. It needs to be rotated about the x-axis 90 degrees. So I'll snap that down to 90 degrees. And now I want to translate it along this axis. The piston I need to move as well. So I need to rotate it 90 degrees, translate along this axis. And then on the base is the first part that I'm going to start working with. So I'm going to get this connecting rod moved out of here. And then go from there. Okay, so I'm going to go ahead and fix this. This will be the fixed constraint when I get into motion simulation. So I'm going to go ahead and, so what's the last constraint I added was a fix. So I'll click that, and now that's fixed. And now I want to put the crankshaft in, so that's going to be a concentric, which will map over to the motion simulation just fine. Okay. I do want to go ahead, is that thing clocked correctly? Yeah, that's clocked correctly. So I don't need to rotate this. So what I do need to do is get the connecting rod in place, so that's going to be another assembly constraint, concentric. I'm going to pick that edge, and the connecting rod's where it's supposed to be, and it's in the right configuration. So this would be at bottom dead center for the engine. So okay. And now I need to get the piston in place. So again, I'm going to add an assembly constraint between that edge and that edge. And note that I don't have a wrist pin in this. You could add a wrist pin. It's not really necessary for the motion simulation unless you want accurate forces. If you want accurate forces, then you are going to have to model these things as complete as you can with all the little details and set the material properties correctly. So that looks good. Now I need to get the sleeve in place, which the sleeve's kind of interesting. You might think you'd use a concentric constraint. I haven't had good luck with that in NX with this assembly, so what I'm going to actually use is a fit constraint, but I want to get the sleeve lined up first. So what I'm going to do is I'm going to put a concentric constraint in and then delete it. So I'm going to use that to get the cylinder where I want it to go. Okay, and then I want to come over here to constraints, and I'm just going to go ahead and delete that constraint. It's kind of cheating, but it works. And then I'm going to move the sleeve up where, so this is bottom dead center. I want it obviously I'd have to precisely align this, but I want to make sure that I've got a little bit of room from the bottom of the piston to this, and I can check clearance as this thing rotates. So that's where I'll leave it for now. Now I need to actually have the constraint between the piston and the sleeve, so I'm going to do an assembly constraint. I'm going to do a fit. I need to select the outside surface of the piston and the inside surface of the sleeve, so I'm going to click that, and then I'm going to wait till that shows up and do face and piston. Okay, and now that should be in there. I want to do a test run of this in the assembly just to make sure that my constraints look good. So move component, I'm going to select the connecting rod, put the handles up, and then, or sorry, the crankshaft, and then I'm going to, I forgot to fix the sleeve, so I'm going to cancel that and add my assembly constraint to fix the sleeve. Alright, now let's try that again. Move component, crankshaft. Okay. Yeah, now it looks like an engine. So obviously I don't have the cylinder head in there, and this sleeve is not correct. I'd have to chop this off more or less flush with the top of the piston in this. But this basic setup will work for as detailed parts as you want to go if you're doing this for real. I do need to go ahead and set materials at some point in time, so I'll do this now. I want to go ahead and save this file before I do much more. So I'm going to go to Menu, Tools, Materials, Assign Materials, and I'm just going to go through these and set the material properties, which will include the density, which is required for accurate forces and motion simulation. I'm going to set this piece, so I'm going to go ahead and set my material. Let's just do a steel. Let's call it 4340. Oh, sorry, I forgot that I actually have to open that up first. So let me open the base. So I'm just double clicking that to make it the work part and then going through that process that I just went through. I'm not sure why it's so picky about it, but it's kind of annoying, but it works though. So I set the material. I'm going to go ahead and set a different surface material for that so it looks different. So I'm going to go to System Materials over here, and I can pick from all sorts of different materials. These don't really have anything other than an aesthetic effect. So if I want to say brushed steel for that, then I can just drag that material onto that part and just kind of think about it for a little while. I'm going to pause it while it's thinking. Okay, that just took a few seconds. So note, nothing happened. So to see what happened, you need to change the display setting to, so rendering style, you want to go Studio. And on a modern PC with a graphics card, this really shouldn't be an issue, displaying this and just leaving it in Studio basically as you're working. I haven't had any trouble with it. Depends on how complicated your mechanism is. This, in the grand scheme of things, this is a very simple mechanism, so I can Studio shade all this stuff and it'll look fine. You can always set it back to the other options if you're having performance issues. Okay, so that's that part. I want to go back to Assembly Navigator, back to the engine, and I want to repeat this process for all of these things. So I want to do the rod next. I want that to be made out of aluminum. So let's do 6061. That's not the best choice for a connecting rod. Actually, a aluminum connecting rod is going to fatigue at some point in time. But anyway, you can set it to a real material. I guess let's just do 4340. That's safer. Even though, again, this isn't a real engine. So I'm going to pick that, 4340. Okay. I want to set a display. Let's just do iron. That works. Again, it's just a display. It doesn't actually change any of the properties for the part. I'm going to go back to assembly, double click on my assembly, and I'm going to go ahead and do the rest of these parts that same way. I'll pause it for now and then come back once I'm done. Okay, I'm back and I have all the materials set. So I set a surface material for it, so the components look a little bit different. And I've also set the actual material for these. So in case you're wondering when you set the physical material for motion simulation, most of what it needs is the density. It needs the density to calculate the mass of each of these components, and also the inertia tensor. So it does, for any kind of 3D motion simulation, it has to calculate the inertia tensor, which saves a huge amount of effort. Actually trying to do that yourself, for those of you that have had dynamics, is for stuff like this, it's almost a nightmare, especially for even more complicated parts. So it uses the density and the geometry to calculate inertia tensor and save you a huge amount of time. So I've got everything set up and I'm ready to take this thing into motion simulation. I'm going to go ahead and save this real quick. And then I'm going to push it to motion sim. And as before, the first thing I have to do is come over here to the Motion Navigator and create a new simulation. I want to do dynamics because I want to do the kinetics in addition to the kinematics. You can see some of the options you have here. I have not done a flexible body before in this. I'm sure it makes things an order of magnitude more complicated. But feel free to try it out and see what happens. I might do an advanced motion sim later on that covers that, but I'd have to learn how to do it myself first. So motor driver, I haven't had much luck with. I've tried doing that. There's an option to simulate a brushless DC motor, but it doesn't really seem real complete, and I can't find any information on how to actually use that. And you could also, as I'll show today, you'll also be able to use functions and inner functions to drive motion. So you really don't even need that in there if you have the equations of motion for whatever the driving component is. So I don't really need to check any of these things. I could name it if I want to, but I'm just going to click OK. Note that it tries to map some of the joints over. So it did the base to crank, crank to rod, rod to piston, piston sleeve, and that looks okay. And we'll do a real quick test simulation, just put a driver on this thing and see if we can get it to move. Sometimes that works, sometimes it doesn't work. So note that it's complaining that nothing's grounded, so it didn't map the fix to ground, so I will have to do that. And see, it wants to ground the crank, which is a terrible idea. So I'm just going to click no. It's thinking okay, and now I want to see what exactly NX has done here. So those are all links, which is good. Joints, that looks okay. I need to go ahead and ground a couple things. Let me do that and see if it works. So I'm going to go home. I'm going to put some joints in here. I want to fix the base. And note it wants a coordinate system for this. So I just want to let's do the x-axis. Okay, and now I want to fix the sleeve. And I'll do the x-axis as well. Okay, so now I should have the joints I need for this. I've got revolutes there, and note as I click these, you can see it shows what they're between. So that's the base and the crank, crank and rod, rod piston, and then the piston and sleeve. So let's see if this does what we want it to do. So I need to add a driving motion, otherwise it's just going to work under the effect of gravity. So let's go ahead and put just a regular rotation on this and see what happens. So I'm going to drive. I need to drive a joint. I want to drive the joint between the base and the crank. I want to do, so I can just put a constant in here. I want to, since this is an engine, I want to do an RPM basically. It's going to be in degrees per second. Note I can change this to revolutions per minute. So let's try 1,000 revolutions per minute. Actually, let's do a nice number that's divisible by 60 and multiply. Just an easy number that's divided by a lot of things. So I'll use 1,200. So that'll be 1,200 RPM. Okay. And then I'm going to do a real quick solution. Oh, I got to create a solution first. I forgot to do that. So I need to, over here, set up the solution. Normal run, kinematics, dynamics. Here's the time. So 1,200 RPM, that's going to be, 20 times per second. So I need to set that to 1/20th of a second. So 0.04 seconds. Let's do 100 steps. Gravity, here's where I can pick gravity. So I want to go ahead and set that to be the correct direction, assuming this engine was oriented with this direction being down as shown. Gravitational constant in there. So meter per second squared, that's correct. And then, okay, now let's try solving this. Okay, so note that it's found a couple of redundant constraints. Basically what's going on is you have this fit constraint in the cylinder, that cylindrical constraint in there, and that actually provides a couple of redundant constraints. The moments mainly between the piston and the rod. It's okay, it just gets rid of the redundant constraints. You could kind of go through the process of getting exact constraints for this, but it doesn't really matter. It gives you correct results in this. So you can just dismiss that, just to understand why there's redundant constraints from the cylinder fit between the inside of the bore and that, and then these concentric constraints in here. So it solved it. I know it looks like nothing happened. If I do animation and then play, I should get a full rotation of the crankshaft. Well, I missed a little bit. I think I should have done 0.05 instead of 0.04, so I can fix that. So actually I need to go edit the solution, so I need to come over here. I want to solution attributes. Let's do 0.05. Yeah, that's correct actually. 1/40th is 0.05. I should have used a calculator on that. So let me solve it real quick. Dismiss that animation. Now I should have a full revolution. Yep. Note I have it set to loop. If I did one way, it would get to the end and then just stop. I could do back and forth rocking, which might be interesting for certain mechanisms that basically rock, so like a rocker crank type setup. But it's a little weird for this, so I'm just going to leave it as looping. And I've got a nice piston cylinder engine here, and I can check for clearance visually. You can do that automatically. That's a little more advanced, but I can certainly do it visually. I can move it to the highest, the most interference point, and then go from there. So it works nice and well without interference. I'm going to go ahead and close this. Okay, so now what I want to show, this isn't too much more than we did with the beginning tutorial. What I want to show now is how to add, excuse me just a second, sorry about that. I want to show how to add a couple of the extra force options we have here. So note we can do a spring. This does not have, so to simulate air pressure in this, I'd actually have to add some kind of spring to this. So if I click spring, you can see the attachment here. Note I can add to a slider or a revolute joint for a rotary spring, or I can do link to link. So for example, I can go from action and base. So action, I want to act on the top surface of the piston, and you can see the dot that shows where the force applies. That's relevant. I mean that matters for the spring distance, the spring stretch basically. And then I can do the base up here. And then note that I can do an expression, I can do a spline, I can do, so if I do shortcuts, it just shows these, by the way, if you ever saw that and wondered what it did. So it just basically changes this to little icons. So for an expression, if I just want to do a spring constant, that's newtons per millimeter. So that's 10,000 newtons per meter. So that's a relatively stiff spring. We'll try that and just see what happens. And then I can set preload. Free length is calculated based on the distance between those 2 points. So you want to, for this case, set it at bottom dead center. Note that I can also create a damper at the same time. So it already has a number in here. So if you don't want a damper, you need to uncheck that or set this to 0. So we'll leave the damper in there. So since this would be an air spring in real life, obviously a linear spring would not work. So if you want to actually set this as something more complicated, you can do a spline, and then you can actually type the function in here. There's a function manager where you can save some of these things and bring them back in. So I can create new, purpose, motion, stiffness, and damping, and with the reference in there, and you can go through this process and create any kind of spring you want, basically. Okay. So within this dialog, this is a little different dialog than NX has, that you've probably seen before. These are the different steps you have to go through. This is the ID, so this is where you said it's motion, stiffness, and damping, where it's going to be saved. And then reference and response. I'm not exactly sure what those are. I think they're just part of the identification. Click this. This gives you the X and Y spacing. So this you can do real. Note these are grayed out. They don't work with this function type. Even spacing on the X and Y. And then I can actually go to X and Y and define a function. So there's some pre-built things. So if I just want noise, I can click noise, and it's going to give me basically 1024 points in noise. I can do a harmonic, so sine wave, sweep, and all sorts of other things, which would be pretty helpful if you had certain oscillating loads. So, or I could just put a function in from scratch, basically. Since I don't have one here, I'm actually going to close that, and then I could do key in from text editor, and here is where I could enter data basically from any distribution I wanted. So I could use the ideal gas law to create, for each value of x here, I could create the y variable that corresponds to that. Since I don't have an Excel sheet or anything like that for me, I can't enter it today. I'm going to cancel that. You can also import from a spreadsheet. I'm not sure exactly how that's going to work. I've clicked that button without never having clicked it before. But okay, there we go. So I'll be able to actually use the sheet in Excel, save that, and send it back, which is very, very handy, actually. So in short, you can basically enter any kind of relationship you want for a spring like that. You'd have to do a little bit of modeling before time, but I'm not going to use that in the simulation. I just kind of wanted to go through and show you where those dialogues are. But all I really want to do is just put a spring on there for now. Spring damper. Okay. You can see it adds little icons there. And I'm going to go ahead and solve this again real quick. Animate, and the animation's actually not going to look any different because since I've driven this joint here with a motion, not a force, then basically the kinematic, it's kinematically forced. So adding these springs and the stamper is going to change the forces involved, but it's not going to change the rotational speed. If I drove this with a constant torque, then the accelerations would change, and I'll show an example of that in just a bit. So what I want to do now is go in and just look at some graphs. So I'm going to go to XY graphing, create a new one. I want to pick a joint, so I'm going to look at the the base reaction forces. Actually, I want to look at the joint. So the joint between the base and the crank, I want to look at force. I want to do force magnitude, and I want to add that to my chart. Okay, and let's just go new window, and you can see the magnitude of the forces operating on the crankshaft itself. I'm going to go ahead and close that. So if I want to turn that spring off, I can actually come over here and uncheck those things, solve it, reopen that chart, and now I get different numbers for the force in the crank. So once you've created a chart like that, it's saved. I can turn these back on, solve it, and bring that back up. I just realized I forgot to do something in that. I was looking at the chart and it wasn't changing, and it took a second to figure out what I did. These actually, unchecking these just hides them. What you actually need to do to disable them is to right click and deactivate. I forgot that's a little bit different in Motion Sim than it is in other parts of NX. So now hopefully I solve it and I get different numbers. Yep, very different numbers. So note, without those forces, I'm somewhere max out. And again, the font here is ridiculously small, but somewhere around 37 newtons. And then if I reactivate these things, now I get giant numbers. So over about 1400 newtons at the top end. So you can just create these charts, but just be aware, if you want to save a chart, though, you actually need to get the data out of NX before you update this chart, because whenever you redo the simulation, it overwrites that data. So just in case you want to keep the data for this before you do something else, NX integrates with Excel very nicely. I just need to right click on this, plot the spreadsheet, and amazing things will happen here. Just a second. So it connects automatically. If I go to the sheet, then I have the time step. I have the degrees of revolution of the joint. I have the, and then it crashed, of course. Let me close that and redo it and see if I can keep it from crashing. So I'm just going to plug. And it broke. Okay, let me diagnose this and I'll be back. Sorry about that. NX hard crashed. I had to Control-Alt-Delete and close the process. So I'm going to try to do that again, and hopefully it won't crash this time. So I should have that in there, and I should just be able to, since it has stored the solve, so I should just be able to send it to the spreadsheet this time, and hopefully NX does not crash. Before I do anything with this, I'm going to try saving this. I'll just put it on the desktop. Okay, so now going back to this, I've got all the data saved. I've got the force absolute, and I've got my data saved, and I've got it in Excel, so I can keep this and do multiple runs and then compare them within Excel. So I'm going to go ahead and close Excel now, and hopefully I get back to NX without it crashing. Okay, I did. So a little buggy. I don't know if there's a single CAD program that doesn't have its little quirks like that. So don't be too freaked out if something like that happens. I was able to save the file, even though NX was throwing a repeated warning that I couldn't close. I was able to go up and file save, so I didn't lose any progress. But it's not a bad idea to save often when you're dealing with these CAD programs. I think everything, I've heard from people that basically use everything, and they all crash at some point in time. NX is better about that now than it's been in the past, but you're still probably going to see some crashes. There's just so much going on. I mean, when you think about all the different things a program like this can do, it's pretty amazing, and it's yeah, there's always going to be bugs. But anyway, I got the data out of it, so, and I had the part saved. So so that's most of what I wanted to cover in this tutorial. So adding springs and dampers, doing functions, or just adding splines, or just any kind of arbitrary data to force it. I guess the one thing I need to do is show how to drive this with a force. I've always driven it with kinematics. So what I'm going to do is come up here to the driver, and I'm going to deactivate that. And then what I'm going to do is apply a torque to the crankshaft as opposed to drive it through kinetics. So I'm just going to do a scalar torque. I'm going to drive this same joint, so joint 1, and I'm going to do Newton meters, and let's just put 100 Newton meters on it. And now solve. and now when I animate it, it should look quite different. So it's intermittent. It's not intermittent, but it's a non-constant angular acceleration. It's quite fast though. So if I wanted to try to determine what the RPM was, what I could do is, or just see what the RPM's fluctuating around at. I need to add another graph over here. So I could open the one I've already got, and I have no idea what it's going to look like. Yeah, it's crazy. So I immediately, looking at this, know I need to have more time steps. So that looks really bumpy. So what I'm going to do is I'm going to go to edit my solution, and I'm going to do an order of magnitude more steps. It's going to take a little bit longer to solve, but not that much longer. So just think about the time it takes to do this by hand. It's kind of infuriating, really. I mean, all the time you spend in dynamics learning to solve things like this, and NX can churn 1,000 data points out in about a second. But especially though, whenever you're moving up to, a real engine, if you're doing a V8, this is really the only way you can do the analysis in any reasonable amount of time. So let's see what my chart looks like now. A little bit smoother. So I'd probably want to do a time step investigation on this. I'd do it, basically do twice as many steps and see if the result changes. But what I really want is RPM, so I need to add another graph in here. So let me do new. I want to, let's see, I wonder if the joint will give me what I want. So let's do velocity, angular magnitude, put a graph in, put it in a new window, and see what we've got. So it's 0, so that's not what I wanted. Let me actually delete that. Let's go new. Let me do the crank, I believe is what I want actually. And I want velocity. I don't want angular magnitude. I need to make sure my axes are lined up. So I need to get this Rx, Y, and Z corresponds to the coordinates of the joint, which the coordinate screen's not shown here. So I'm going to do this a little bit trial and error. Actually, what I'll do is I'll put these all on the same graph, and that will let me figure out which one it is real quick. Yep, it is. I wish they'd make the font bigger. There we go. So it's the green, it's the Z axis. So the other ones are 0, of course. And you can see it's fluctuating somewhere around an astronomically large number, because this is in degrees per second. So you'd have to convert it down to RPM. But you could throw this into Excel and look at the data and chop off this initial. But it does settle out, though. Since it does have a damper in there, it is going to settle out nicely at some specific speed. So with that external torque on it, that's what it settles out at. So obviously this is incredibly powerful. If you're designing an engine like this, you could use this to help with balancing. If you had accurate numbers for the forcing functions on it from, if you're just doing the just with air in it, you'd have to model the air, the air spring effect, and also the damping from that as well, because it's never going to be adiabatic. Also, if you're actually modeling a combustion cycle, you can model that pressure as well. You can model it as the spring. You could model it as a function of the X change, which you could convert to angles of the crankshaft. You'd have to pre-convert that before and then put the data in from an Excel spreadsheet. But as I showed earlier, it's really not bad doing that. So very, very powerful, and you can save the data right to Excel. So, and I think it only integrates with Excel. It just kind of automatically pops up Excel. It doesn't really give you an option. So even if you're not using Excel for your final data processing, you could take it into Excel and then save it as a CSF, comma separated, and then send it to MATLAB or whatever else you want to look at the data in. So that's it for this tutorial, and I'll go ahead and stop it.